Brace yourselves for a cosmic cataclysm of unprecedented proportions. Betelgeuse, the red giant star poised on the edge of our galaxy, is sending ominous signals through the universe. Using the James Webb Space Telescope, astronomers have uncovered something profoundly unsettling about this colossal celestial body. As renowned astrophysicist Brian Cox issues a grave warning, the question looms: are we on the precipice of witnessing a catastrophic supernova explosion that could forever change the night sky as we know it? Let's dive in. In the grand tapestry of the cosmos, where stars are born, live, and die in spectacular fashion, one star has recently captured the imagination and concern of astronomers and the public alike. This star is Betelgeuse, a red supergiant of immense proportions and age, situated conspicuously in the constellation Orion. Its distinctive reddish hue and variable brightness have long been a source of intrigue, but recent developments have intensified interest in this celestial giant. As we explore the nature of Betelgeuse, we find ourselves on the cusp of a potentially monumental event in the life cycle of this star. But what could these changes signify? Are we witnessing the prelude to a cosmic spectacle of unimaginable scale? Betelgeuse, approximately 764 times larger than our Sun, is a stellar behemoth. Its colossal size is almost beyond human comprehension. Imagine a star so vast that were it to replace our Sun, its surface would extend beyond the orbit of Mars, engulfing Mercury, Venus, Earth, and Mars in its stellar embrace. This incredible size is not just a testament to Betelgeuse's physical attributes, but also speaks to its stage in the stellar life cycle. As a red supergiant, Betelgeuse is in the twilight of its existence, a phase characterized by expansion and cooling following a life spent fusing hydrogen into helium in its core. But what about the age of Betelgeuse? This star, believed to be around 8.5 million years old, is relatively young in human terms but ancient in the context of stellar lifetimes. Its current red supergiant phase is the culmination of millions of years of stellar evolution, a period marked by dramatic changes and processes that have transformed it from a hot blue star to the red giant we see today. The life cycle of stars like Betelgeuse is a story of transformation driven by the relentless forces of nuclear fusion and gravity. Betelgeuse's distinctive reddish hue is another hallmark of its current stage. The red color results from its relatively cooler surface temperature compared to other stars like our Sun. While the Sun's surface temperature is about 5,500 Kelvin, Betelgeuse's cooler surface registers temperatures around 3,500 Kelvin. This cooler temperature allows Betelgeuse to emit light at wavelengths that give it a red appearance. This color is not just a visual trait, but provides clues about the star's physical condition and the processes occurring within its vast gaseous expanse. Adding to Betelgeuse's mystique is its historical color change. Ancient Roman and Chinese writings suggest that around 2,000 years ago, Betelgeuse was yellow. It was only in the 9th century that Arabic scholars first described it as red. This color shift over human history is not just a detail in the annals of astronomy but a clue to the star's evolutionary path. The variable brightness of Betelgeuse is another intriguing aspect. It's a semi-regular variable star, which means its light periodically waxes and wanes, and this variability is a characteristic dance of luminosity that has fascinated astronomers and sky watchers for centuries. Typically, Betelgeuse undergoes a 400-day cycle along with a longer cycle that stretches about 5 years. These cycles have been documented as far back as 1836 by Sir John Herschel and possibly even earlier in Aboriginal oral traditions. But what makes Betelgeuse truly enigmatic is not just its changing brightness but its irregularity. Unlike many stars that follow a predictable pattern, Betelgeuse occasionally deviates from its rhythmic dimming and brightening, hinting at complex and less understood processes occurring within its colossal form. Recent groundbreaking revelations about Betelgeuse captured the attention of astronomers and stargazers worldwide with an unexpected and dramatic change in its appearance, an event now famously known as the Great Dimming. In late 2019, the red supergiant Betelgeuse, one of the brightest stars in the night sky and a prominent feature of the Orion constellation, began to mysteriously dim. The star's dimming was so pronounced that it began losing its luminosity at an average rate of 0.01 magnitudes per day, reaching its lowest brightness in February 2020. Betelgeuse, normally visible to the naked eye even in light-polluted areas, became markedly fainter, a change noticeable even to amateur observers. However, there's one problem with trying to monitor the activity of Betelgeuse: the time paradox. When we look at a star like Betelgeuse, we are not seeing it as it exists in the present but as it was in the past, due to the time it takes for light to travel to us. In Betelgeuse's case, at approximately 725 light-years away, the light we perceive today left the star nearly 7 centuries ago. This time lag makes it challenging to predict and monitor sudden changes in a star's behavior, as we are essentially peering into its past. The Great Dimming event served as a reminder of the inherent difficulties in real-time astronomical observations and the limitations of our understanding when dealing with the vast cosmic scales and the time paradox they introduce. The unfolding of Betelgeuse's celestial drama was closely monitored by Andrea Dupree, Associate Director of the Center for Astrophysics at Harvard and Smithsonian, and her team. They utilized Hubble to analyze the behemoth star as part of a 3-year study to monitor variations in Betelgeuse's outer atmosphere. These observations offered a unique insight into the dynamics of a variable star like Betelgeuse, which regularly expands and contracts, causing fluctuations in brightness. Hubble's sensitivity to ultraviolet light allowed the researchers to probe the layers above the star's surface, which were heated partly by the star's turbulent convection cells. Further analysis of the Hubble spectra taken at different points throughout 2019 and 2020 helped in measuring the movement of material in Betelgeuse's outer atmosphere. In particular, the spectra focused on magnesium-2 lines, which are indicative of the star's atmospheric conditions. These observations showed material moving at speeds of about 200,000 miles per hour from the star's surface into its outer atmosphere. This hot, dense material eventually extended millions of miles from Betelgeuse and was the precursor to the dust cloud that led to the star's dimming. Dupree and her team estimated that about twice the normal amount of material from Betelgeuse's southern hemisphere was lost over the 3 months of the outburst. This mass loss was significant, especially considering that Betelgeuse, like all stars, continuously loses mass, albeit at a rate far greater than that of our Sun. The scale of this mass ejection and the subsequent dimming sparked discussions among astronomers about whether this event could be a precursor to a supernova explosion. The proximity of Betelgeuse, about 725 light-years from Earth, adds to the intrigue, as any such explosion would be visible from Earth and provide a rare opportunity to observe a supernova up close. Yet the question remains: what does this dimming event portend for Betelgeuse's future? Is it an indicator of an impending supernova or simply a unique episode in the star's long and complex life? Several theories have been proposed to explain this sudden change. One prevalent theory suggests a phase in the supernova explosion process, a hypothesis that gained traction due to the common belief that Betelgeuse is nearing the end of its life. Another popular theory implicated dust, possibly from the star itself, obscuring our view. Betelgeuse, like other red supergiants, is known to shed material, and it was thought that this material could form a dust cloud dense enough to dim the star's light from our perspective. A third explanation considered changes in the star's photosphere, the visible surface layer, which could affect its apparent brightness. In-depth analysis using various observational methods helped unravel this mystery. Spectroscopic studies indicated a drop in Betelgeuse's effective temperature, suggesting that the dimming could be due to a large dark spot on the star's surface. This theory was supported by the observation that Betelgeuse's temperature dropped by at least 170 Kelvin around the time of the dimming, pointing to significant changes on its surface. In the end, the key to understanding this unusual phenomenon came from humankind's sentinel in outer space, the Hubble Space Telescope. Hubble's observations revealed that the dimming of Betelgeuse was most likely caused by a significant ejection of hot material into space. This material formed a dust cloud that obscured a portion of the star's surface, effectively reducing the amount of light reaching us from Betelgeuse. The dust cloud was believed to have formed from superhot plasma, which erupted from a large convection cell on the star's surface and then moved through its hot atmosphere to the colder outer layers. As it cooled, it formed dust grains, creating a cloud that blocked light from about a quarter of the star's surface. Hubble's ultraviolet light spectroscopic observations, which began in January 2019, were crucial in piecing together the timeline leading up to Betelgeuse's darkening. These observations captured signs of dense, heated material moving through the star's atmosphere in the months preceding the dimming. In December 2019, several ground-based telescopes also observed the star decreasing in brightness, particularly in its southern hemisphere. This material, which was initially more luminous than the star's normal brightness, eventually led to the formation of a dark cloud as it moved outward and cooled. The hypothesis was that this outflowing material and the resulting dark cloud caused the star's sudden dimming. The scale of this ejection is truly monumental, propelling Betelgeuse into an astronomical spotlight. The star expelled an estimated 400 billion times the mass typically released in a standard solar flare event. To put this into perspective, this mass ejection is comparable to a supernova explosion, reinforcing the notion that Betelgeuse could be approaching a crucial phase in its life cycle. Despite the dramatic events unfolding around Betelgeuse, the supernova scenario remains a matter of debate among scientists. Some argue that while the dimming is a significant and intriguing event, it may not necessarily foreshadow a supernova. Red supergiants like Betelgeuse are known to go through periods of increased mass loss and brightness variation without necessarily culminating in a supernova. The star's fate will depend on various factors, including its internal dynamics and subsequent observations. Although the cosmic spectacle we have witnessed with Betelgeuse is mesmerizing, it is also a reminder of the dynamic and unpredictable nature of stellar evolution. As we continue to observe and analyze this fascinating star, we may uncover more insights into its future and the broader processes governing the life and death of massive stars. The cosmic dance of Betelgeuse is far from over, and we are merely spectators to its grand, unfolding story. The ongoing saga of Betelgeuse offers a unique opportunity to deepen our understanding of stellar evolution, particularly the life cycles of red supergiants. While the recent Great Dimming event has certainly captured attention and speculation, it is important to recognize that the star's story is far from complete. Here are some additional insights and implications of this cosmic phenomenon. The significance of Betelgeuse's dim event. 1. Stellar Evolution Insights *. The Great Dimming provides a rare glimpse into the late stages of a massive star's life. Red supergiants like Betelgeuse are in a transitional phase, and understanding their behavior helps astronomers piece together the complex processes leading up to supernova explosions. By studying the changes in Betelgeuse's brightness and the ejected material, scientists can better understand the mechanisms that drive these massive stars toward their final act. 2. Observational challenges and techniques *. The time paradox and the need for precise observational techniques highlight the challenges astronomers face. The distance of Betelgeuse means that our observations are essentially looking back in time, making real-time monitoring difficult. Advances in observational technology, including space-based telescopes like Hubble and future observatories, are crucial for tracking such events with greater accuracy and for potentially predicting similar occurrences in the future. 3. Comparative analysis *. Comparing Betelgeuse's behavior to other red supergiants and stellar phenomena can help establish patterns and predictive models. For instance, how does Betelgeuse's dimming compare to other red supergiants that have shown similar variability? Are there common threads that could indicate an impending supernova, or is Betelgeuse an outlier with its unique set of circumstances? Future observations and research. 1. Monitoring the star *. Continuous observation of Betelgeuse using both ground-based and space telescopes will be essential in determining whether the Great Dimming is a precursor to a supernova or a different stellar phenomenon. Future observations could provide more data on the star's luminosity, surface changes, and ejected material, shedding light on its evolutionary trajectory. 2. Theoretical modeling * Researchers will use the data from Betelgeuse's recent behavior to refine theoretical models of red supergiant stars and their eventual transition to supernovae. This modeling includes understanding the physics of material ejection, dust formation, and the impact of these processes on the star's luminosity and structure. 3. Broader implications *. The study of Betelgeuse also has broader implications for our understanding of stellar populations and the life cycles of massive stars. Insights gained from this star can inform our knowledge about other similar stars and the frequency and types of supernova events across the universe. Public interest and education. 1. Engaging the public *. The dramatic nature of Betelgeuse's story has captured the public's imagination. Engaging the public through educational outreach, Media coverage and interactive platforms helps foster a greater appreciation for the complexities of astronomy and the dynamic nature of the universe. 2. Citizen science * encouraging amateur astronomers and citizen scientists to participate in monitoring and reporting observations can enhance the data available to professional researchers. Community involvement in tracking variable stars and reporting findings contributes to the broader scientific effort. Conclusion: a cosmic spectacle. Betelgeuse's recent Great Dimming event stands as a testament to the extraordinary and often unpredictable nature of stellar evolution. While it has sparked significant interest and debate, it is also a reminder of the dynamic and ever-changing universe we inhabit. As we continue to observe and study this enigmatic star, we gain valuable insights into the life and death of massive stars, the processes that govern their evolution, and the broader cosmic phenomena that shape our understanding of the universe. The story of Betelgeuse is a cosmic narrative still unfolding, and its chapters will continue to captivate astronomers and sky watchers alike as we unravel the mysteries of the universe.